Okay, I want to talk to you about Bohr diagrams, which should be review, and Lewis dot diagrams, which might be review. So for a Bohr diagram, the first thing you have to do is you have to grab your periodic table. Yeah, go and get it. And it should be the one that your teacher has been using so that you become familiar and comfortable with all the things that you can find in your data booklet or your periodic table. And the first thing you're going to do is you're going to look up sodium. And you're going to notice that a sodium has atomic number 11, so it's going to have 11 protons. Sodium's atomic mass is rounded to 23, so the number of neutrons is going to be 23 minus 11, which last time I checked is 12. And sodium, because it doesn't say ion, sodium is neutral, and therefore the number of electrons is, oops, what am I doing? The number of electrons must also be 11 to balance out those protons. When you're drawing the Bohr diagram, there are lots of different teachers that do it lots of different ways. The way I want you to do it is that I would like to see the nucleus, and inside the nucleus, I would like to see that there are 11 protons and 12 neutrons. So that tells me you can do this. That also tells me that you know that the protons and neutrons go in the nucleus. Then you're going to do your electrons. On a Bohr diagram, in the first energy level, we can have 2 electrons, and that is it. That's maxed out. In the next ring, we'll have the remaining electrons to a maximum of 8. So if I put 8 in here, that makes 10 electrons. So that's maxed out. And then I have 1 more electron to do, so that's 1 electron left. Now you can make your rings go all the way around. You can make your 2 electrons 2 dots if you like. That part's up to you. This is sort of a bit of shorthand to help it go faster, because all we're doing here is reminding ourselves about Bohr diagrams, not actually learning about Bohr diagrams. So that's how you do a Bohr diagram for sodium. The new part, or maybe new part, are converting these into Lewis dot diagrams or Lewis electron diagrams. To convert this into a Lewis dot diagram, we're not going to pay attention to the nucleus. We're not going to pay attention to that first ring of 2 electrons. We're not going to pay attention to the middle ring either. What we're going to pay attention to is the last ring. That last ring is called a valence shell, and those are valence electrons. Those valence electrons are what makes it react the way it reacts, have the size the way it has a size. And so scientists are most interested in that last valence electron. So when you're converting this into a Lewis dot diagram, you want to start with the symbol for sodium, which is Na, and then you're going to convert just those last dots here. Is this pen working yet? Nope. We're going to convert just that last dot there, that 1 electron. We're going to put it as a dot or an X to signify that that is a valence electron for sodium. And then we know it has the inner rings fulfilled. It's in period 3, so I know it has 3 wings, 2 and 8, and then 1, but that is our Lewis dot diagram. Let's try again for the fluorine atom. The fluorine atom, grab your periodic table again, look up fluorine. It's number 8, and therefore it will have 8 protons. Its atomic mass is 19. Oh, I'm sorry, it's 9. 9. The atomic mass is 19 minus that atomic number of 9, so that makes 10 neutrons. Electrons, because it's an atom and because it's neutral, it will have to balance out those 9 protons, so it'll have 9 electrons. To draw the Bohr diagram, I'm once again going to draw the nucleus, and in that nucleus, I'm going to have 9 protons and 10 neutrons. Then I'm going to have 9 electrons total, a maximum of 2 in that first ring, then I could put 8, but I don't need all 8. I only need 7 more to make up those 9 electrons. And I am done for the Bohr diagram. To convert that into a Lewis dot diagram, we're going to put an F for representing the fluorine, and then I'm going to look at those 7 electrons. Now, adding a layer here. You can't just put the 7 randomly, okay? You have to put them in 4 boxes first. So sort of think about it as like north, south, east, west first, and then I can start to pair them up. So there's 4 electrons, 5, 6, 7, 8 if I had it, okay? So you can see I have 3 pairs and 1 by itself. Now, there are more ways to draw this. I could have, if I wanted to, I could have done 1, 2, 3, 4, and then paired this one up, paired this one up, paired this one up, and left this one blank. Doesn't really matter which quadrant has it blank. That is up to you. But you must have 3 partners and 1 by itself. So there are technically 4 variations here, could be. These guys here are called the pairs. The ones that are paired up are called lone pairs. And this one by itself is called a bonding electron. And that's because it is the one that's going to bond. It's lonely, it's all by itself, it is the one that is unstable, and it will want to form a bond in order to partner up and become more stable. So this is a bonding electron, and these are lone pairs. There are 3 lone pairs on fluorine and 1 bonding electron on fluorine. Okay, let's do one more, nitride. Now, the reason I threw this example in is because of the IBE. The nitride tells me I'm talking about an ion. So far we did an atom and another atom. Now I'm talking about the nitrogen ion. So when I look up nitrogen and I look to see its ion, it's in group 15. So because it's in group 15, therefore it'll be a 3 minus, because 5 plus 3 is 8. So a 3 minus. So the symbol for nitride is going to be N3 negative. Okay, so I look up the periodic table and I find that it is atomic number 7, and so it'll have 7 protons. Its mass is 14, so 14 minus 7 is 7 neutrons. From the 14 minus 7, maybe I'll stick to what I did up the top. And the number of electrons. So it has to have a 3 minus charge. I'm not allowed to change the protons at 7. Therefore, I must have 10 electrons for my nitride. Ooh, hold on a minute. There you go. 10 electrons for my nitride. Okay, so we're going to rearrange this whole thing so that you don't have a glare, maybe. Nope, glare it is. I'm actually going to draw it up top. How about that? I'm going to erase these, and I'm going to draw it up here so you don't have that glare. Okay, so I have in my nucleus, for my Bohr diagram, in my nucleus I have 7 protons, 7 neutrons in my nucleus. Great. Then I have 2 electrons in the first energy level, and then I have, remember I have to get to 10, so I have 8 electrons in that last energy level, and lastly I have to tell the reader that it is a 3 minus charge. Okay, so now I'm going to convert that into a Lewis dot diagram. The Lewis dot diagram is going to still have the symbol in the middle. I'm going to put the 3 minus as brackets like we did up here. So I have the N in the middle. I have to have 10 electrons. I'm only going to do the valence shell. So that would be 1, 2, 3, 4, 5, 6, 7, 8. 4 lone pairs. And overall, it is a 3 negative charge. So now here's a top tip. Your anions will always be full and your cations will always be empty because they lost that electron when it was an atom. So it'll always be an empty Lewis dot diagram at the shell, and a anion will always be full in order to achieve that full octet in order to be stable. Okay, so hopefully that gives you a good overview on how to draw Bohr diagrams and Lewis dot diagrams for metals, nonmetals, and ions. Have a go at practicing some of your own.